was telling was I'm fascinated about the self-organized criticality that you've worked on. And so this is very interesting to me because it's been, people have come and touched it, maybe once or twice every decade and left it down until you picked it up in 2018, 2019. So what was the story behind that? Like, how do you get there?
Yeah. Thank you for the opportunity, first of all. I appreciate self-organized criticality has been talked about a lot since the early 80s, I think. And then I hope I'm not going to be one of those that touches and just leaves it.
Sure.
Right? But I think this one is here to stay. Even I would say we need to change the paradigm because of it. And it's not just in traffic, all right? And it's really in all civil engineering. And that's might be news to you. But yeah, I mean, it's a new way of, not new, right? It's a different way of seeing these problems they all have the same thing in common. And it's that they're complex systems. It boils down to that. It's very simple at the end. There's so many economics, earthquakes. It's like you name it. Every system that is interesting or that it's challenging, and therefore that we're still studying it, right? In all sciences, they all tend to be complex systems because we cannot yet figure them out, right? So, yeah, the case of traffic is of my particular interest, of course. And the way I came to it was during COVID, actually. It has something to do with COVID being a complex system and the way diseases spread, right?
Okay.
I mean, we're in the same boat as all of those things, stock prices, right? These, and they're all unpredictable. That's the common feature. You can call it chaos, unpredictability, power law dynamics, but complex systems is like the umbrella term. So yeah, it was like a juncture of things, right? Being able to think more, I guess, by myself. We're confined in a room, right? I don't know, something clicked, and really deeply. Started reading a lot of physics. Yeah, this is all grounded on physics from the 80s, actually, until the 2000s. And of course, it keeps on going. And subjects like KPZ, hopefully we'll get that.
Okay, yeah.
To touch that.
I'd love to, yeah.
All the KPZ universality stuff. I mean, there's a lot of progress being made in maths right now, in the area of probability theory, that is, in all these systems. Yeah, and actually they have a lot to say because all the math is based on these TASEP models from physics, the particle hopping models, they call them, right? So TASEP is the one that corresponds to traffic flow. The more general is ASEP, so it's asymmetric simple exclusion process. It's a very standard process or model for physicists. But the nice thing is that traffic, and when I say traffic, I mean the simplest model of traffic, right? Like the kinematic wave with a triangular diagram, for example. Traffic is a special case of those models, and it's called TASEP, right? So the T is totally asymmetric, so all particles go in one direction, right? The more general is there's a probability that particles go either way, right? But in traffic, you just want to go down that link, right? So yeah, and so it turns out that the mathematicians and physicists, they figured out so much about that model, which turns out to be the model of traffic.
Okay.
Right? So there's a lot to dig in now to extract all that knowledge all these years, which really nobody's looking at.
So what is it called?
totally asymmetric.
Yeah. So I don't know if this is the right place to ask this question, but in your papers, you compare this process to random walk, right? In some sense, and like the random walk, I know. Now, how does that fits into the asymmetric nature of this?
Yeah. Okay. So the random walk, you're talking about a self-organized criticality paper, right? Yeah, that's the way the random walk appears in traffic is through the variational theory put forth by Daganzo some years ago, which in mathematics, again in physics, was known as Hopslack's solution to the KPZ equation, actually. Right, we can talk about Daganzo later. He rediscovered many things, which shows his true genius, actually. All right, but anyway, so the random walk comes from that variational inequality, variational formulation of traffic,
I'm missing up with you. Sorry.
Yeah. Which boils down to a minimum path problem in the time-space network, right? So you have your time-space network with these lopsided networks that Daganzo calls them, and it boils down to finding the shortest path. Okay. Now, when you are at the critical density, right? So average density of vehicles, it's around the tip of that triangle, and you add a noise, like a Brownian, like a normal white noise, you can call it. Yeah, that would be the correct term. White noise. It turns out that minimum path problem that you're solving, the cost of each path is a normal random variable. It's because you're minimizing a random walk at the end of the day. It's like the cost function, right, is a random walk, basically. It's a strange. But right, so in variational theory again, you try to find your minimum path to the boundary of the initial data.
Sure.
Right? That's where you want to get to. But it turns out when you have the critical density, excuse me, and with some noise, then all the points at that boundary you want to reach, they all have the same cost. And it's normally distributed and everything like that. And this is where criticality comes in. Because if you ask the question, then what is the length of the traffic waves, the stop and go waves, right? The congestion spreading back, right? If you want to know like the lifetime of jams, that becomes a power law distribution. Just because it's a random walk, so the length of a jam, the duration of a particular jam, corresponds to the time where you hit the same value of the random walk, right? So you're going up and down at some time, you stabilize at a point. The time until you reach the same level, it's known to be a power law with exponent of 0.5, which is crazy. It means that there's no mean or variance or anything.
Nothing is defined, essentially.
It's the nightmare scenario.
Okay.
And some people might know Nassim Taleb. Several terms, the black swan, lately anti-fragility, which is a pretty nice concept. And in one of his books, talking about the statistical consequences of fat tails, he has a chart of the different distributions, right? So you start with the normal distribution, central limited works and everything is fine. So there's a scale, you go then to the exponentials and the log normal and the power law with this exponent, being around 2 or 3, which is fine. But then when that exponent gets smaller than 2, you lose variance. When it's less than 1, then you lose the mean, right? And he calls them, the ones that are less than 1, he calls them the forget about it distributions.
Okay.
Right?
That's interesting.
He jokes around. He says, if you ever stumble upon one of these, you just, close your eyes, go home, have a breakfast, just forget about it. That's how bad these distributions are. And unfortunately, with the recent data by I-24 back in Vanderbilt in Tennessee, our recent investigations show that indeed we see this type of behavior with an exponent around 0.5, which I'm still trying to wrap my head around, because it's really, you couldn't ask for bigger data set or more comprehensive data.
Sure.
Right?
Sure, yeah.
I-24, it's a huge project. So yeah, I'm still looking into it, to verify these results, but it looks like, and maybe no wonder why traffic has been so complicated to tackle. It's because it's the nightmare scenario in terms of distribution of something. So it's a complex system. It's little humans can do to a point.
So this is fascinating. So essentially, the situation is the situation that anything can happen depending on where you are right now, right? The future. So, would you say controlling it is a meaningless effort, or it requires something different than what we have today?
Right. Right. I think, with human type of control that we've been trying all these years to, you can do so much. There's, either light congestion, something that you can control still, right? In some networks where you have, your big avenues one way and it's well designed. Control is going to have a good impact, The problem is in big cities. Think Beijing, New York, big cities. What happens in big cities is like transportation networks tend to a limit in terms of cities, and networks and congestion spreading and capacity and all that. And this limit, there's little you can do actually. Even if you have the best control possible, it's in terms of average travel times or average congestion for everyone, there's really little you can do. Even if you have the best AIs, I guess, right? It's just because there's a limited capacity. Yeah.
So
now, if you talk about more microscopic things like capacity drop on freeways, control is really helpful.
Sure.
But freeways don't live in a vacuum. Right? They cross cities.
Right. So that's when we do ramp metering and we have a spillbacks all the way through the city, right?
And ramp metering is promising, but it's the spillback problem that negates all the benefits. Yeah.
And this is very interesting to me. I never thought about it until I read your papers, because in your paper you have you have shock waves and jams within jams, essentially, and this is what we observed, and this is puzzled me for quite some time in terms of, okay, how do you measure a traffic? How do you say this is a traffic jam and not this one? Because there's a jam that's propagating up, and there's all of a sudden another one within it, and you characterize it in some sense, right? So how does that connect to all of these from a sense to all the chaos and criticality point?
Right. The keyword here is fractals.
Okay.
Yeah, that makes the connection, right? Because jams within jams, and within jams to infinity, that's the fractal rate. That's one of the ways that we generate fractals.
Yeah.
And whenever there's fractals, there is power loss. They go hand in hand because they're the embodiment of the scaling variance. So it's the invariance of systems to changes in the size of the system. Right? So you, like a mouse, if you scale it up, to the elephant size, right? They're not going to look the same. There's going to be an exponent different than one. But anyway, that's kind of. So whenever there's a fractal, there's going to be a scaling variance. There's going to be these power laws. Okay, and again, these powers, depending on the exponent, you're going to have chaos or not, right? And chaos is when this exponent is around 1, right? When you don't have the variance, right? That's why it's in, you cannot predict it, but there might also not be a mean, right? Around 1, right? By the way, people might be familiar with Zipf's law for the frequency of words in a given body of text, right? That's the same exponent. That's the power law with the exponent of 1, right? So it appears in nature repeatedly since old ages. And we still haven't tackled that question.
So does this go back to that? I don't know if it's relevant or not, but you have this discussion about the elementary cellular automata, and you talk about that rule 184. Is that right?
Right.
Is what we are seeing in traffic essentially. So I don't quite grasp the concept from the connection between them. So how does this? So if 184 is traffic, so there's no other way that you see like 195 in traffic, or there is a particular system in the world that is only with 195.
Yeah.
Is that the right assessment of this?
Well, the world of these cellular automata is an open question. Yeah. So by the way, the 184, there's only 256 of them, right? 184 corresponds to traffic because it corresponds to TASEP.
Okay.
But TASEP with deterministic TASEP. Because in TASEP you have a probability of hopping to the next cell.
Okay.
Right? And 184, that probability is 1. If it's empty, you're going to go. That's how it works.
Okay.
Right? So it's a special case of TASEP. It's a deterministic kinematic weight model at the end of the day, right? And then, okay, so that model is deterministic, but traffic obviously is not, right? And we see that in the data and everywhere. So the latest theory, let's say, is that it's like 184, but with a tiny probability of slowing down, you can call it, like tending to zero. It's because if it weren't zero, it shouldn't be a power law.
Sure.
What we said was power law, the duration of dance, for example, because people have shown that gives you just normal distributions.
Okay.
When you have a noise, like a normal noise to this 184, but if it's zero, if that noise is zero, then you get the power law, right? The power laws we're seeing in real traffic now with this new data. So it has to be the case that it's in the limit of that probability going to zero. It's very interesting. And I reached out to the math people that are doing these derivations, and they don't know yet. I mean, I haven't asked everyone, but
sure.
I mean, there's a very good Chilean mathematician, which I'm going to meet with him next week, actually, next month.
So is this very active area in math?
Yeah.
Or?
KPZ is very active now in probability theory math. And
okay.
Yeah, not so much in physics lately, but it was back in the 87 when it came out. So yeah, that's the latest theory. It's a vanishing probability.
Okay.
Right. Which is nice to me because it kind of brings together the school of thought, let's say the deterministic world, right? The Berkeley school, with the Gonzo, right?
Yeah.
And then let's say the more physics community, Nagel and, Herman, right? All this. Which thought, which believed that it was a critical phenomenon, right? Complex system, we call it now. But there was some randomness, right? And there was this big fight back in the day. But if we're saying and seeing empirically that the solution is somewhere in the middle when that probability goes to zero. But still, it has to be stochastic, right?
This is interesting. I'm going to go back to that for a second. So in your analysis, you introduce a one-lane road, and this randomness that you're introducing has specific characteristics to it, right? So I was reading this, and I was wondering how that translates into a regular roadway or a two-lane road, let's say minimum. So, because a lot of these instances, like at some point, I remember like Cassidy showed this, that a lot of these waves are happening because of lane changing vehicles, right? So, so how does that translate? Because not all of them are random behaviors. A lot of them are predefined behaviors from individuals' perspective, right? Yeah. So how's that connection? Because you see them on I-294, so right. I-24. 24.
Yeah, there's this. Yeah, it's a full-fledged freeway segment. But that's one of the wonderful things about these theories. It's this concept of universality. And simply put, it's like really nothing matters. Sounds dismissive, but only very few things matter. Like lane changing, and of course I'm talking about big picture questions, right? There's details like lane changing and OD matrices even that don't matter, right? If you look at as a high enough altitude in the microscopic day-to-day operations, right? You need to. It's going to be helpful to account for lane changes and the effects of that, right? But somewhere in the middle, when you ask those interesting questions, what's the capacity? How much it's going to cost to do this or that? Details tend to blur and tend to not matter so much. I started working on lane changes back for my dissertation and everything. We explained capacity drop, among some other things. And those things are important at an isolated level, right?
Right.
And that's I think a big trend now, that we need to step out of isolated intersections or isolated freeways or isolated whatever. It's all connected, right? And it's such a big network, and big networks tend to the same limit. The KPZ network, I'm going to call it.
Okay.
And we're not taking advantage of that.
So this troubles me, but in a good sense, troubles me in a good sense. So.
Yeah, I've been troubled all
yeah, so because you've done a lot of simulation of networks, right? It takes considerable amount of resources to do a simulation.
Oh, yeah.
And we are really, the only thing we are interested in is that point right at the top of the fundamental diagram, because that's where things matter, right? The rest of it we don't really care about. Would you say, I don't know, maybe you haven't looked into it, but would you say like, if I do these simulations 1 million times because of the fat tail of this parallel, I still might have something that I've never seen before? Would that be a right statement?
I'm afraid so. But for some, that's the tricky thing. Not all variables you might be interested are going to be heavy-tailed, right? It's the problem arises in the micro when you want to control the system, the day-to-day, because you don't know if the link is going to be congested in the next 5 minutes. You just can't predict that. That's the thing. When you're at the tip of that diagram, right? If it's very light or very congested, it's very easy to predict. Right? But yeah, it's at the critical point. Yeah. That's why it's called critical density.
Okay.
They knew it, but they never explained us why.
Yeah, that's true. Can I be a little bit more sort of controversial here? Because this is very interesting to me from a sense that the breakdown point has always had its own value, but it's always been sort of a black box, right? So this is and a lot of the studies is focused when they're dealing really with fundamental diagram and development and everything. It's focused on what is happening after it, right? When it's become congested, like 3-phase model and like the whole idea that there's no fundamental diagram and everything else, right? So, but what you suggest here is those don't really matter not really don't matter, but don't matter as much as the fact that we don't really know anything meaningful about the system when it's at the breakdown point. So focusing on what is after it might not matter as much. Would that make sense at all? Or
yeah. It's the nature of chaos. Yeah, it's right, and then comes the trouble. The additional trouble is that this problem is so pervasive, and we're not teaching it. I'm really troubled with that, and maybe we can talk about later about education and civil engineering.
Sure,
in particular.
Love to do that.
Yeah, maybe later.
Yeah. No. Yeah.
So yeah, let's get the traffic. Yeah, and you were mentioning on the effect of these details. We don't know what happens at the critical point, right? But again, I mean, there's things that you will be able to predict at a higher scale, like average travel times, during that period. Big averages are still going to be, I guess, attainable. The distributions are not going to be normal, right? But people know what they are already, right? These mathematicians and the new normal is it's the Tracy-Whittem distribution, which I bet you haven't heard of before reading the paper. Right?
No, I know.
Right.
And this is very interesting to me from a sense that it seems to me whatever matters is not really a normal distribution.
Right. Yeah.
But we treat everything as normal most of the time.
Exactly, and that's one of the big problems right now. We believe the central limit theorem too much. Right? It was supposed to be, for independent events.
Yeah.
Right, and we took it for granted because I'm not sure why. Maybe because it's easy to teach, right? I mean, sell again. Nobody proves it, right? Because it's very difficult.
Nobody proves it. No.
But the applications are good, and it has had a good service over the years, right?
Yeah.
But until, I guess, the Industrial Revolution, I guess, right? When things started getting interesting, correlations started to happen, and the problem seems difficult, right? But at the end of the day, everything, all these networks that have this type of, that are like transportation networks, tend to the same distribution, this Tracy-Whittem distribution, right? It takes the place of the normal distribution, and it's not fat-tailed, right? It looks a lot like the normal. It's like a little bit skewed, though. So yeah, I think that's the part that's already done, and that we need to take advantage of and apply in our knowledge. Yeah.
So Wendy, this might be a very dumb question. Do you think there's a transition from the normal into this one?
Yeah, right. So when congestions, when demand grows, so at the beginning of the rush, there's no congestion, everything is normal. Yeah, normally distributed. Right, but then demand increases, right, and you start getting to that point. Yeah, it's going to be a transition between the two, I guess.
Okay.
Yeah. And I mean, it's a difficult problem, right? Because this distribution arises in the long-term, big system size equilibrium, right? Which is not, we're not going to attain it, obviously, in that 2 or 4 hour rush hour period.
Sure.
But still, it's we need to try it out and see how it how it compares with data. And
So this is interesting because you show in your papers that the existing data from different cities actually do match this at this scale, right?
Yeah.
So, but those are not for one day. Is it the correct statement?
Right. Yeah.
Right. So, how does that work?
So you're talking about the macroscopic fundamental diagram,
Right.
Right, for cities.
First of all, is there a connection between the two? Because you're looking in the other paper, you're looking for like a variational theory, you're looking for one lane, infinite length, and everything, right?
Yeah.
Is there a relationship between the two?
Yeah. It's the 184. That's the common thread.
Okay.
Right. So, excuse me. So in the self-organized paper, we showed that it's critical, right? It has all the ingredients for a complex system type. And in the other, we said, okay, if it's critical, basis phase transition theory, then it has to be the case that the MFD, excuse me, is a power law, has the shape of a power law, right? And you can kind of confirm that, or that is equivalent to say that what they call the coexistence curve in chemistry, which, I'm not a chemist, so, but it kind of tells you the relationship between when a fluid is going to go from liquid to gas, as temperature changes. But if you see the shape of it, it looks just like a fundamental diagram. So the coexistence curve is typically temperature on the y-axis versus density of particles. In our case, it's going to be flow versus density, right? So in the paper, all I said was that the temperature should be the flow. If those two concepts are going to match, right? And actually that unlocked all the theory that was already laid out by Nagel in 2000-ish. Yeah. So
essentially they got that part different, right? So that's the only thing that
right.
Sort of.
They didn't postulate what the temperature could be. And if you really want to get controversial, we can talk about the two-fluid model.
Okay.
Right, because that's the only other published interpretation of temperature.
Sure.
Regarding traffic flow, right? So, Nagel in the 2000 papers, they said traffic is a phase transition. We just need to know what the temperature is in our case, right? All right, so curiously before that, right, the Prigogine and Herman paper about the two-fluid model, right, and their kinetic theory. So it was before Nagel, actually. But they postulated something similar, right? And they said that the temperature was the speed, actually.
Okay.
The speed of vehicles. And actually, it couldn't be just by the dimensional analysis perspective. Temperature is energy, right? Which should be speed squared, not just speed. So I think, and that's the controversial part, right?
So I haven't read their paper. I wish I did, but so there's a relationship between flow and the speed, right? In some sense. So, and so where does this okay? How do I put it? So there's a relationship until they're at a critical point when there's no relationship in some sense, right? So is that where their interpretation fail?
In a sense, they started a little bit like Nagel. They said traffic is a phase transition. But they call it the Einstein-Bose transition.
Okay.
Or Bose-Einstein.
Yeah.
But then they said, okay, the temperature parameter is going to be the speed. So quite like the same idea. Nagel just said, I don't know what the speed is, later he proposed the noise as the speed, but it's not. But yeah, so that's why it's inconsistent in that way. And maybe that explains why this model is not so popular. I mean, they invested a lot of resources, right? These are really smart people. A Nobel laureate, right?
Yeah.
But yeah, maybe that was the problem. Maybe the data didn't fit for that reason. It would be interesting to see if a comparison, to see if that was really the problem, or maybe you can still interpret temperature as a speed, and some other interpretation might be possible. But yeah. So going back to the flow interpretation, right?
Okay. Yeah.
So going back to the coexistence curve, if you look at the fundamental diagram of a city, they look just the same. So that's kind of the intuition behind it. Right? All right, and if it's going to be critical, at the critical point, everything is a power law. That's what's so fascinating. That's an assumption, right? That everything diverges as a power law, but it turns out to be.
So there's no proof for this, but every observation we have shows it.
Yeah.
Okay.
They cannot prove it mathematically, if you will. But yeah, it works every time.
I haven't done research in the at the network level, really. So at least not to the level that I wish I had. But there's the concept of hysteresis even at the network level, right? So how does that translate into the two-fluid model? Can that be captured when there's loading and unloading in the system? How does the phase transition work? Because the fluids will go back right on the curve, I assume. But traffic doesn't always do that. Or maybe it does, I don't know.
Yeah. Well, I'm not an expert in the two fluids, so I wouldn't know the predictions in this case. But of the general traffic model, hysteresis is a complicated subject. You can see it because of many factors. Yeah, the most common is loading and unloading, right? And it's, once you understand why it happens, you see that it's really an artifact, right?
Yeah.
I mean, it's the same people going back and forth. It's just the way, the history that accumulates in the network, right? And gives you a different path when you observe it macro, right? So it's a natural thing that should happen in every good model, let's say.
Okay, yeah.
Now, one of the good things about all these ideas is that a good model doesn't have to be complex, right? Complexity comes from simplicity. I mean, it's a mislabeled term, I think. It should be simplicity. That's the case in traffic, right? 184 is the simplest possible model of any type of non-trivial computation, right? And yet you see all these, this complexity. Yes, in that sense.
This is a very interesting concept. Because you see, since like 40 years ago, a lot of computation power we have, like compared to what we had, right? So it's very easy to increase complexity now. It's very easy to say, well, I'm going to add 200 more parameters to see if I can capture this because, well, I have all the computation I need in the world. So, and people, I think it's more of it. There's a clear tendency to go, well, okay, let's make it more and more and more complex to see if we can do it.
Yeah, and that's the other term, complexity, right? So we add more parameters to the model, right? I mean, it increases the complexity, that's right. But the thing we need to remember is that you don't need to get complexity, you don't need to do that. You can maybe do the same task with far fewer parameters. Yeah. On the other hand, we wouldn't have ChatGPT and all this breakthrough. Right?
That is true.
Because that's another phase transition or critical system, right?
Yeah.
So at the level of number of parameters up to 2018, I guess, or 19, we weren't seeing much, right, out of these models, right? But you cross the limit, this critical number of parameters, and then you start seeing all these things that people are calling almost AGI. You know?
This is a very weird topic to discuss. I can go on for the whole night, but I saw some high school kids and their teachers told them to use pen and pencil to write the essays in the class, so they can't use ChatGPT. And say, well, okay, maybe it's good for a high school, but I don't even know it's good for high school. But come on, I mean, it's like telling, you know, I'm pretty sure 1950s they would tell people to not use calculator, and right, so we moved from that, and
it's going to be a wild transition. I envision also a possibility of a drastic reduction of number of professors, right?
I mean, if there are not enough courses to teach,
Yeah, and then if people don't like or don't want to, learn these fundamentals, because everything can be done by the AI sort of thing. You know? These are all super important questions. But right now, I want to focus on the complex system.
Yeah, so this would fit probably there.
Yeah,
because you're right at that point.
the tipping point, right? I'm not sure how much success I'm going to have, because right now the trend is to reduce the number of courses in the curriculum, right? So to add one more, I don't know. One possibility is maybe to replace statistics. Statistics is a topic that's getting old real quick because of all this, right?
Yeah.
And mostly because there's not a clear connection between statistics and these machine learning models, right? I mean, there's regression is the best connection.
Yeah.
You can claim AI is regression is the type of AI, right? But other than that, I mean, in AI, you never talk about t-distributions, the significance of parameters.
Yeah, you don't.
Totally irrelevant question.
Yeah.
Right, for some reason. So, it's not really, very little statistics in the machine learning, day to day, let's say. So, up to what point we keep teaching these materials, right? Which is basically the central limiter. That's statistics. And as we were talking, it's just, I mean, it was relevant, but not anymore. I mean, it's like a basis. I mean, you have to know it. So what I do, because I teach stats for undergrads. So what I've done in the last few years is just split into that. So in the first half of the course, I teach the basics, central limiting basics. And then I try to go into these complex systems.
Oh, that's interesting.
Yeah, and they seem to like it a lot. So
I would imagine.
I'm really encouraged because,
it's not an easy topic to teach either.
I mean, you can make it easy. I mean, nobody's teaching it. That's where in civil, right, or engineering, and even in physics. I mean, here there's not a course that's called complex systems. It's still you learn it after you graduate, I guess, right? That's been the expectation, which I think it's a real disservice to our education. So the concept of fractals, for example, that should be high school. I mean, no, K-12, somewhere in there. Yeah, since, I hope you appreciate now the importance of fractals, right? It's the key between all these ideas.
Yeah, no, this is fascinating. And they just show it to you in K through 12, right? they never give you the details of it.
If you're lucky, you got it shown to you. I never got that shown to me. Yeah, I mean, it's just fascinating, and they're so beautiful. Some of them, right?
It is.
There's
Yeah,
so
I mean,
to see. I mean, it has all the elements for a fun lecture.
I was really amazed when I was trying to read all of these. The first thing I went back to some of the references, and I went to that the Solar Automata Nature paper.
Yeah,
and that was really interesting. I mean, that you have these 256 rules that are governing everything in some sense. And it's just fascinating to see like things that completely independent from each other, and they're still governed by the same thing. I'm really looking forward to see what will come out from your research in the future. This is so your papers are all in my course for students to read. Yeah, so I added them because I mean this is like very interesting stuff for people, and for some reason we don't have this kind of fundamental research that often happening in recent years in transportation, right? So a lot of focus, maybe it's AVs are to blame, but a lot of focus has been on simulation. So
yes, right. But don't underestimate simulation. Huh?
Yeah, no.
Simulation actually, we didn't talk about this, but one of the implications of all these things is that you don't want to use models that aggregate stuff at some level, like the cell transmission model. Right, it's known to have a lot of error, numerical error.
Sure.
Right. And yeah, in part, I think that was a little bit to blame of why we didn't realize this before. Because if you run models with the cell transmission model, for example, on a network and you try to control it, everything's fine. Everything works great, right? Because there's no criticality. It's deterministic, right?
Yeah.
And then because it aggregates, you lose criticality. That's really key, right? And then the only way out is use microsimulation. Microsimulation is the only one that captures this critical.
Some of this, yeah.
Yeah. And yeah, that explains to me why we didn't, as a community, realize this. If you look at the MFD community, I don't want to get too controversial, right? I mean, they don't have stochastic components. It's all deterministic, right? And then, let me get more controversial, historically, right? So the same argument could be made for static traffic assignment and DTA, for example. Right? Now we know the static traffic assignment is not the right tool for congestion, right? It doesn't capture congestion. Yet we keep using it. And to me, it explains why our cities are the way they are, maybe. Because we use the wrong tools to make decisions. That's assuming politicians listen to what we have to say, right?
Well, yeah, I mean, cities use that, right? That is what they use. DTA is really rare.
Exactly. So we're still using the wrong tools, right? So it's, what can we do? What can we do? Why is, maybe the committee should have like a norm, the traffic flow committee, right? The TRB committee, where we can push for like an arm to push this type of ideas.
I have one sort of a weird question. I want to make these connections in my mind. And so when you talk about the network level, and you talk about seeing these two-phase models and the criticalities still, and then you try to connect all of those through percolation and say, okay, well, this critical density is what is going to tell me what is happening in my network. And how does that connect to the whole SOC idea?
Percolation. Wow. Yeah.
I'm a fan of percolation.
Oh my God. Percolation.
So it's a fantastic concept, but yeah.
Oh my God. Yeah. Actually, it's all percolation. Yeah. It's all about percolation. Should we define it?
Yeah, go ahead. I'd love to, because I'm curious to see how you define that.
So you can either define it at an actual network level or in a time-space network. And that is the same concept. Let's start with the classic network. Percolation, you're going to have your traffic data telling you the speed of traffic. So you can say a link is congested or not. You set a threshold, maybe in density, maybe in speed, right? And you decide whether a link is congested or not. That's one approach, right? And then a percolation, the basic concept is a cluster. And a cluster is just a series of links that are connected because they're all congested. And you can go from one to another through that cluster, without touching a free flow link, for example. So it's all the links that are connected and congested in that case, right?
Yeah.
And then percolation, it's like a synonym of flowing through the system. So the system percolates when that cluster spans the whole network and spans the size of the system. And that's your critical point, right? It's when that cluster, they call it the giant cluster or the infinite cluster, right, starts to grow, diverge in size as a power law. And there's an exponent for that.
The size of it, right?
Yeah, the size that tends to infinity, right? And then you're going to have a distribution of clusters. That process of the critical point, when you achieve the critical point, is when your cluster is spanning the whole thing, right? Now, in the time-space diagram, you can define a similar network. So you just take one link, right? Then you have time-space diagram, right? So time and space in the axis. And now you imagine this network, which looks like a grid. That's where you solve the shortest path problem that we talked about before in traffic. And in that case, you're going to have these. Let's think of the CA 184, right, where you have a cell. The time-space diagram is a grid, like an Excel spreadsheet, right? And in each cell you have a density or a number, right? Is 0 or 1. 1, there's a car. 0, there's not. And you can define the cluster similarly, right? So, but in this case, is cells, right, next to another cell with a 1, meaning that there was a car, right, in those two cells, and they're connected. So cluster in that case is like a traffic jam that's, spills back. And then, the number of cells that it encompasses measures the size of the congestion of that, right? And it's actually the delay that creates. Percolation, it plays a role in both ways, right? So in the latter one, it's directed percolation because you have time that only goes forward, right? So it's a different universality class, they call it. At the end of the day, it's just different exponents for these power laws, right? So directed percolation has one set of exponents, and the other, the regular percolation for the network, has another set of exponents. Yeah, and actually we're working on a bit with Monica on network percolation. So she published one in Nature Communication, I think, with Marta Gonzalez and Lucas Zambo. Very interesting paper looking at, I think it's the first one looking at percolation at the network level in this sense. I know you have some work.
I've done some work on the communications network,
Right.
and that is not unique. There are a few people that papers that I based my work on them. So my introduction to percolation is through my wife. She did percolation in her postdoc when she was in University of Manchester. But this is very. When I was reading your paper, and I remember I remember reading Monica's paper in Nature Communications. I don't think I read it as detailed as I read yours, but this was very interesting because my wife's work was a two-flow thing. So you had for the oil displacement, you had oil and you push water from different directions to move it out, and like that was like the percolation for them. And they modeled it. But what I noticed was the just similarity between them. The way you load your network is very similar to what she does, because that she's loading the system with water and pushing the oil out. And this is very interesting, especially if you have a confined system that your water pressure is different from different directions. Now, at some point, the oil has to go out somewhere. And now the whole thing is going to be very well defined through percolation, because now the one that has the higher pressure is going to push the water out and push the oil out and not let the water in, but because it's not compressible. But traffic is a little bit compressible in some sense, right? Sort of. And there's similarity and differences, because and I don't know how to look at this, because from the network perspective, we usually start the congestion right from the middle, from the downtown, and we spread out, right, sort of. And for my wife, it was like it's more of from outside to inside. But then you can look at also from not percolating traffic, but also the opposite of percolating, the voids in the system.
Right. So,
and they both can be defined as far as I understand. Maybe I'm wrong here, but with the same set of equation in some sense. So when you do this, when you look at this critical density and connected component, and which here's where I was quite puzzled in terms of if you say my critical density is 0, everything is going to be one component, right? So everything at the beginning of network, right? Yeah. So how do you figure out what is your exact critical density? Right. So you increase it eventually until you have congestion.
Yeah. Actually, we don't know. Right. There's been very little work on this area. Right? It's just starting. So the first paper I mentioned by Monica and Marta, they defined the critical density on each link separately, as the tip of the triangle, if I recall correctly.
Okay.
So for each link, they defined in that way. Now, then I did a simpler analysis, because I have a conjecture that I need to mention to you. But anyway, so I defined the critical density as, that's the finding, is that it's almost like an arbitrary parameter, because the value that you define, and I use the same for all the links.
Okay.
Right? So you can tune it, play with it, and what you find is that the timing of events changes. So in particular, what they found in the paper, there's 2 percolations that they kept track. One is the network percolation that we discussed, right? And the other one is the flow, is the evolution of the flow, right? So the flow grows in time and then collapses, right? And they wanted to see the timing, when the time between the maximum flow and the network about to collapse, and the percolation, when this cluster starts to span the whole network, right? So those 2 times, and they found that one preceded the other. All right, so they found that, if I recall correctly, that the percolation, right, happens, let me think. Anyway, I think it's before, but it could be another one. right? And then what we show in the other paper with Monica, we're still writing, by the way, is that the way you define the critical density really affects the timing of these two things. So you could have it either ways. And then we identify the parameter that would have the percolation first, and then the flow breakdown, because that's what you want, right? And I think they found the opposite. I forgot. Anyway.
So this is now this is a little bit connecting my head, because it's a little bit weird, because I feel like there might be a connection. This is just me thinking out loud at this point, between what you discuss as, a self-organic criticality, and when the system starts to behaving within that state, and what translates into the percolation, the critical density. So do you think finding that could be saying, okay, here's where the system starts behaving based on a power law? I'm going to pick that as my critical density. Or do you think even we can pinpoint that point? I don't know even we can pinpoint it.
In real traffic, yeah.
Even in the simulation, do you think you can pinpoint it and say, here's where this is happening?
Right. Simulation is 1/2. Yeah.
Okay.
Right. Because you can always treat all these problems like 184 assumes that the diagram is isosceles. Right. So free flow and wave speed are the same.
Yeah.
Right. And that's an assumption you can make. I mean, it's doesn't change anything really. There's a symmetry of the kinematic wave model. But then you were commenting on.
So what I'm thinking is, where you find that, would that be your critical density for percolation?
Right.
Or not necessarily, they don't match.
Right. That's my conjecture. Right?
Okay.
They should match.
Should match.
I mean, the critical point has to be 1. Right. To me, they should match.
My feeling is you can, even if they're different, you can always scale them, right? In some sense, as you suggested in your paper. So a lot of these are similar if you scale them. So it should happen at some same point or around the same point. So.
I think so, but yeah, my co-author doesn't agree, I guess. So we're still debating. But I mean, I think the important thing though is that you can use this critical density as a parameter such that you can prevent collapse.
Okay.
Right. So you can set it such that you see the percolation first, and if you see it, then you can do something and prevent collapse. Right? But and the way they had it previously, I think it's the opposite. Right?
So this is. If I may go a little bit back in terms of the definition of the percolation, if I remember this correctly, so there are two types. There's a side and a bound percolation, right, in the core concepts, and I think these would fit a little bit more into the bound percolation if you treat the links like, sort of. I think it doesn't matter, I guess, but the assumption there is the very original percolation theory was there's a probability of that link being active or not, or whatever we're going to call it, or there with the P.
Right. And
when there's that P to a certain level, then there is a fully connected, like the whole network, right? So, so instead of being occupied, you're saying, okay, so that instead of being 0 and 1, my 0 and 1 is congested versus not congested, right? So now the question is, why you can treat that universally throughout the network.
Right. I think you're referring to, So you laid out the original interpretation of percolation, right?
Right.
That there's a probability, right?
Right.
But you can do the opposite, or the alternative is to randomly generate numbers, let's say between 0 and 1.
Okay.
Right? And then pick those that are greater than 0.5, for example.
Okay.
Right? That's going to turn out to be the same as drawing, like you said before, with P equals to 0.5.
Oh, okay. Yeah, sure.
So you can generate the actual value, maybe the speed.
Yeah.
Between 0 and 1. So there is a correspondence there.
Okay, that's very fun. That's interesting.
Yeah, that's the key step. Yeah, you're right. Now, that correspondence is only there for the Bernoulli case, right? The
Sure.
flipping a coin or
Sure.
probability P. Now, distribution of space, we don't know what it is, right? There might be correlations and everything. So that's where the approximation is, right?
Right.
Because the actual problem is not a Bernoulli trial in every link, right? But what you take from there are the ideas, I guess. The exponents might be the same, right? And that's universality, is that despite being, having different probabilities, maybe, the way the system diverges of that probability is the same for all, right? And that's captured by these exponents.
Yeah, that makes sense. That's actually interesting. So I guess you can just, in the simplest possible way, you can just pick the highest K value that will throughout your network that gives you congestion. That would be your critical density in some sense, right? But it's not necessarily right? So
So I did some numerical experiments, and I think you get the same timing, right? The same critical density, the same critical point for these two percolations I've discussed when you use the critical density equal to the critical density really of the MFD. So if you have the MFD of the network, so you pick the point where the flow is the highest, and using that tends to give you the same timing of the network information and the flow breakdown. So the other point I wanted to come back to related to this is this other implication of criticality. And we touched that a little bit when we talked about the cell transmission model and how aggregating kills criticality, right? So in the paper by Monica and Marta, they used sumo in real networks, very large networks, Sao Pablo, and I forget other two networks. So they were so big that to have decent travel running times, they used the mesoscopic version of sumo.
Okay.
I'm not exactly sure how the model works, but it's not micro anymore. It's going to be meso, more like maybe a cell transmission or something like that. Right? So the results, although they use the actual real network and they have realistic OD pairs, right? It's simulation based, right? And based on a mesoscopic model. So to me, that's kind of a red flag. So
Okay.
We're working on doing the micro simulation of a smaller network, right? Because we still have that big problem.
Is there a way to prove it? To prove that, like, if you run this with cell transmission,
right,
it's going to fail because of this or that.
Right. Like a mathematical proof.
Like, is there a way to do that? Because cell transmission has a very well-defined, right, structure.
Maybe we can work on that.
Yeah, but that would be that's very interesting, Gerald.
So first, I want to make sure numerically that's the case. So I don't know if you've seen the outputs of the cell transmission, but what happens is that the waves are not sharp anymore.
Okay.
Right. It's supposed to be sharp. If you look at the data, like I-24, you see amazing. The same wave speed, all parallel, all beautiful. But if you run a cell transmission model, all you would see is a blur, like a red blur. After a few cells, you lose the sharpness of the waves. And waves are sharp in reality,
Yeah. They're very well defined in the data, right?
It's just amazing. So using this version of sumo, the mesoscopic, what you're doing is that the waves are slowed down. So the effects of things happening slows down. So what they found is that first you have the collapse and then the percolation, I think. And you might explain that with the slowdown of the waves. Right? So the claim is that if you use a micro model with sharp waves, then the two timings should be almost the same, right? Because the waves are going to be so much faster. So the propagation of it's going to be a lot faster. Now that I think of it, maybe then percolation should come a little bit after, right? But maybe not so much after.
Maybe this is some sort of going back to what we started with, but there's this whole concept of synchronized flow. I think Karen introduced it, maybe, right? The three-phase traffic fundamental diagram, everything. So what you discuss in terms of criticality is happening all in that synchronized flow, right? So it's not a point, it's in a region, right?
Yeah.
So, that theory is not well received, I guess. I could say that maybe.
In our community, yeah.
Yeah. So, but then, so I don't really know what happens there, but from a sense that what you said essentially translates, your percolation might happen within that region rather than just right at the top of the fundamental diagram. So it might happen a little bit later.
Right. Yeah. So this synchronized flow idea and his theory, it's really different from this phase transitions that started by Nagel. It's really more based on the empirical data that Kerner observed, and came out with this theory that turned out to be quite controversial. But I think the contribution he made is showing that the congested branch should be scattered, because there's this, he calls it synchronized flow, but it's not really when the traffic, synchronizes.
Sure.
That they have the same speed and all that. So it's more related to this fact that they're going to be in a 2D region in the times, in the flow density diagram, right? Like a stochastic process, really. And that's really what we see, right? Physics call them like a non-equilibrium system, right? It's a system that always, moves around like that. And depending on how you measure it, you're going to see something different, right? Like if your loop detectors, you place them in one position, you're going to be something different.
Yeah, sure, absolutely, yeah.
Or even the how long your intervals are of oscillation, etc.
You also have done some work on it, right? Where you put the loop detectors.
Yeah.
Right, so.
Right. What did we find there? That, right, it depends on, the distribution of the position. If it's uniform, like it's uniform distributed on the link, then the MFD is unbiased. That's kind of a nice result.
Interesting.
Which was first pointed out by Leclerc back in 2011, I think. Yeah, they did something. But where loop detectors are changes what you see absolutely in the MFDs. There's research going on in that direction as well. But going back to all these critical thinkings and Kerner's theory, right? I think this 2D region is spot on, and might be explained by these phase transitions and chaos theory, right? Because they're all non-equilibrium systems.
So at this point, there's no model or explanation for that, right? Maybe there's explanation, but there's no model to say here's how this behaves, right?
General theory.
Yeah.
Self-organized criticality, it's the most likely candidate, but there's no general theory for that either. The original paper of self-organized criticality back in '87 was written by Perback, Tang, I think is the second author, and then Wiesenfeld. And I checked them out, and it turns out Wiesenfeld, he is a physics professor right next door.
Oh, really?
Yeah. So we wrote a proposal together, and now we're working on the topic, which just started this August.
That's nice.
With a physics student and an engineering student. So I hope it's going to be the beginning of.
So we should expect a lot of exciting things coming up. So,
yeah, I mean, I'm hoping for this, getting closer to the physics community.
that's really nice.
Hopefully something good will come up. So yeah, I mean, he's the better position to do like a leap forward in this area. So yeah, I'm teaching him traffic right now, right? So hopefully we get to the same vocabulary that we can figure all these things out. But you're right. I mean, there's no general theory yet. They call it non-equilibrium physics. That's several names. And depending on the area, you would have different methods and all that. But yeah, we're going to zero in on this self-organized criticality.
So are you looking more general as part of this project, or it's really traffic focused?
It's traffic focused.
Okay.
Yeah. But yeah, already the implications are going to be, I think, are going to be a lot more general. So it's connected to turbulence. Right, there's a lot of theory in turbulence and thermodynamics as well. I'll give you another preview. It's not even published or in anything. So we think we found an explanation of Bryce paradox. I mispronounce it. Bryce. You know Bryce paradox?
Yes, the network.
Right.
Yeah.
It says that if you add a link, for example, you're going to make things worse.
Worse, right.
I never believed in that, because the proof that we are being taught, at least in my time, it's just, and it's the original proof, by the way, by guys.
I don't think I've ever seen it proved.
They typically say they show you this network, and then imagine the cost of this link is 2x plus 1, right? And x is totally unrealistic. So. In Daganzo's book, he offers a much better explanation. Right? He talks about the capacity of a freeway breaking down if you reach the critical density, right? And that made a lot of sense to me, right? Because it might be the case if you have a network, and if you put a link, then you're going to get this on-ramp congested earlier, for example, right? And it's going to increase the cost, So yeah, but yeah, if you, because interpreting temperature as the flow opens the door of a full analogy with thermodynamics, okay, and it's one of the other things. And so we found that entropy would be the travel time, for example. It's really 1 over the speed. It's like the pace.
Sure.
It's the travel time of 1 unit distance, right? That's the entropy. Right? So we're grappling with that. And it turns out that, Bryce paradox, so if you add something to the network, you're increasing the number of possible states of the system, which is the definition of entropy.
Yeah, that's
right?
That's interesting.
Okay? So that makes a lot of sense, right? You add a link, therefore you increase the options in a way, right? That increases the entropy, and the entropy is travel time. So it's super direct, right?
Yeah.
So that might be a physics-based explanation of that paradox.
That's interesting. I think that paradox has been around for so many years.
Probably 80 years.
Yeah.
So yeah, that should be a fun paper to write.
Interesting. No, this is all fascinating stuff. Yeah.
And then work, which is the main thing in thermal. I think it's network production. Some people in MFD are always considered, right?
Yeah.
It's the number of people in network times the speed. Right. So and heat is the Newell surface. The Newell surface is like the cumulative count curves. That's the heat in this case. Yeah. So I'm learning so much physics and having so much fun. Which is why I think we need to put more physics in engineering. It goes against the current. But, one of the first things that Carlos Daganzo told me when I joined the graduate program at Berkeley is that you have to think like a physicist.
And we used to have a lot of physicists in transportation, right?
Yeah.
And back in 90s and early 2000s at least, and many of them don't do transportation anymore.
That's right. And Nigel, for example.
Yeah. And helping Nigel, none of them,
Triber, he's not as active, but he's still there's still some, but you're right. There's hopefully with this there
could be some some interest from the physics side as well, right? So
I'm trying to.
Interestingly enough, UC, the physics department is within the College of Engineering. So
it's very smart.
That's very interesting, and
that explains why you guys are number one consistently.
I don't know, but this is very interesting.
That makes a lot of sense.
I don't know who came up with that idea, but
by the way, so the civil engineers get physics course.
They do get physics course.
Apart from the elementary physics.
Well, you can take them. There's no requirement for it.
Yeah.
I don't think there is. My students take a lot of quantum computing courses now. And it's accessible. So
UC played an important role in complex systems. Stephen Wolfram.
Oh, okay. I don't think
so. He's the founder of Mathematica, the computer model.
Yeah, I know the name, but I don't think I didn't know that. UC.
Yeah. He worked there in the 80s.
Okay.
But then he retired, quit, I guess, and founded Wolfram Research.
Interesting.
You use Mathematica? That's all I use these days.
That should be fun.
Computations.
That should be fun. Anyway,
he's one of the originators of complex systems. So he founded the first complex system journal, back in the 80s, based on this idea of simplexity, let's call it, right? These simple rules, that was around the time he wrote that Nature paper on cell automata. Right? So he developed all that theory of cell automata and worked in UIUC for, I guess, 10 years or something.
Yeah. That's very interesting.
And his headquarters is in there, in Urbana.
Oh.
Mathematica, We should pay a visit.
Maybe we should, I should,
I'm hungry, I guess.
Yeah, no, thank you so much for taking the time. Appreciate it. So I want to encourage whoever's going to listen to this to go to your Google Scholar page and read your papers on criticality. These are fascinating stuff.
And also, reach out to me if you want to write a paper. If you're a physicist.
Okay, sounds good. Yeah. Well, thank you so much. Thank you.
All right. Thank you for the opportunity.
Yeah, thank you.